taught it yesterday was this. You have to figure out first the order of all the transformations that are going on. And I said it's kind of like PEMDAS in that do whatever transformations are in parentheses first, then whatever's being multiplied, and then whatever's being added or subtracted. So the parentheses in this problem are actually the square root, right? That's grouping stuff together. But the thing is that there's two things going on inside there. There's the +2 and there's the negative. Do you remember I told you yesterday which you do first? 2, right? So you do horizontal shifts first before you do reflections, which is what that negative is. So then the very first transformation we'll talk about is the +2. But since this is an insider's lie, that means you go left 2. And then the negative x, is that a reflection over the y-axis going this way back and forth, or over the x-axis? The y, right? Because since it's attached to the x, it means you're changing the sign of the x value. If it was +2, now it's -2. If it was -5, now it's +5. So it reflects it this way. So that's a reflection over y. And that's the two things inside the parentheses, okay, inside the square root. The next thing is any multiplication. Well, what do we have being multiplied by? The 3, okay? Now, if you're multiplying values by 3, is that a stretch or a compress? It's a stretch, because multiplying by 3, you're multiplying which values by 3? When you have a number out here, what are you multiplying by 3? The x's or the y's? The y's, right? And so this means whatever your y value is, multiply it by 3. So if your y was originally 1, now it's going to be 3. So it stretches and gets longer and taller. And then after any multiplications, you take care of addition or subtraction. So we have this -1 out here. What direction will that go? Does that mean to go? Down, right? So that means down 1. This is an arrow. And so here's what I would do. I would graph the parent function first. So the parent function for square root, the 3 main points are 0, 0, 1, 1, and then 4, 2. You skip over to 4 because when you square root it, you get a whole number. You get an integer. So that one's easy to work with. So 1, 2, 3, 4, and a 2. So this is the parent right here. Let me highlight the axes so that they're easier to see because they kind of blend in. So now what I'm going to do is those transformations on each of those 3 points. So you might want to follow with your eyeballs so that you can see what I'm going to do. So starting with 0, 0, I'm going to go left 2. And so that gets me right here. Good? Now reflecting over y means this is like a mirror, and when you reflect over it, it has to be symmetrical. So if I'm currently 2 to the left and I'm going to reflect this way, how many do I need to be over here? 2. So if instead of 2 to the left, now I'm 2 to the right. So I'm right here. So that's the reflection. So now I need to stretch by 3. What is the what is the y value right now? Okay, and what is 0 times 3? 0, so I can stay there. And then I have to go down 1, so it's right here. This is the initial point, where it is now. Okay. So then I'm going to now do all of that for the 1, 1 point. So 1, 1 is here. I need to go left 2. 1, 2 is right here. I need to reflect over y. It's 1 this way, so a reflection over would get me 1 this way. So that puts me right here. Okay, that's mirrored. And then I need to stretch by 3. Well, what's the y value right now? 1. And what's 1 times 3? 3. So now I'm going to go up to the 3. And I'm here. And the last thing is down 1. So right there. Okay. And then the last point, so I'm going to do all of that with the third point now. So I'm here. Left 2 is right here. The reflection over y this time is different because I'm on the right side of y now. I'm 2 to the right. So to mirror it or reflect it over, I need to be 2 to the left, right? So that's right here. And then you stretch 3, so you multiply y by 3. What is y right now? 2. And what's 2 times 3? 6. So that gets me here. And then you go down 1. And that's my transformed graph by doing each individual transformation in the right order. I think, as much as I can gather so far, that this is how you might have been taught in pre-cal or pre-AP Algebra 2. Because what makes this problem tricky is that there's 2 transformations under the square root. That's what's making it tricky. So if you were taught to factor out the -1 that's in front of the x, and then just count spaces after that, not do the individual transformations, but just sort of use your logic instead, I think you would have done it like this. So, and this is going to be in a different, well, that's not, doesn't really look like a different color. Let's do green. Okay. So factoring out the -1 up there, and the reason why you would want to do that is it puts it in transformation form, which we're about to talk about here in just a second. So transformation form is when it's x minus the h value right here. And so if you're doing insider's lie, or you're trying to take your initial point now, it's 2, 1, which is right here. Okay, that's fine. That's the same. Would you have done a table of, for those of you who did this method before, did you do a table of values next? Because here's what I think you might like to do next. This -1 means you're reflecting it that way. And the next point is 1, 1. So you, instead of going, so you know you're already going this way, you're reflecting. But instead of going 1, 1, there's a stretch by 3. So you're going to go over 1, up 3. And get this point. Okay, right? And then you know you're reflecting that way. Instead of going over the 4, 2 that way, right? Instead of going 1, 2, 3, 4, up 2, you can still go left 4, but now you're doing 2 times 3, which is 6, which gets you right there as well, right? So I'm not exactly sure how you were taught to do, and this is the first year, this is my 4th year with college algebra, this is the first year I've had so many people remember a past way. So I'm not sure if they changed it in the lower maths last year, and that's what you're remembering, or what's going on. Or you just are all so much smarter than everybody that now you remember the stuff from last year. I don't really know. But that's the way you, and this is actually the way I do it in my head, is transform it and then count the places. But I have found that that's not a great method for people who are struggling with visualizing. The doing it transformation by transformation, just point by point, seems to work better for those students. So really at the end of the day, it's what are you comfortable with. If you need any individualized help on the transformations, just meet me at my desk after the lesson and we can go over whichever method you like, okay? I'll be happy to do that. So are there any questions about this right now? Okay, and because I like you, I will tell you that your test review and your test do not have multiple transformations inside the parentheses, okay? Because that's what makes the problems the trickiest, and they don't have that. But it's good for you still to work on them and see it, because it's a challenge. It's a little challenging. All right. So having done the warm-up, all right. Okay. So these are the steps for writing the equation from the graph. The first step says write the general equation for the parent function. I have a list of those for you to the right on your notes. So for example, you can just look like, looking at the I will board, just looking at the shape of the graph, what's the parent function? Absolute value, okay? So you would start by using this general form for absolute value. Okay, that's step 1. And I have all the other ones listed there for you. That's the HK transformation form. The second step is to plug in the special point for H and K. And the special point depends on the shape. Like the square and absolute value graphs, their special point is a vertex, right? For square root, the special point is the initial point, and for cubic and cube root, it's the inflection point. And those are the points we talked about on Monday. The next thing you're going to do is plug in a pretty point for x and y. By pretty point, I mean it's any point on the graph, but you want to look for one that has integer values because it's easier to work with whole numbers than fractions or decimals, okay? So that's what I mean by pretty point. After you plug in those things, you'll solve for the a value. The a value in your equation represents any reflection, stretch, or compress. And then the last thing you'll do is plug those a, h, and k values back into your step 1. Those are constants. Like these are things that will stay the same no matter which point you're looking at. X and y will stay x and y because they represent points that change, variables. So what I want you to do for step 1 here is to just write down the general form. Whatever you think that it is. And I hate this green color. I don't even know why it's one of the default colors. It's so ugly. I'm switching to this color. I know. I need to figure out their settings to fix the default colors. Okay, so did you write this? Oh my gosh. Did you write this? Y equals a times x minus h plus k? Absolute value? All right, good. All right, so that's step 1, just figuring out directly figuring out which general form you need. So step 2, well, we're going to do step 2 and step 3 together. Step 2 was the special point. What kind of special point does this graph have? Does it have a vertex, an inflection point, or an initial point? Okay, it has a vertex. And what's the ordered pair for that vertex? 1, 2. Okay. And is that going to be our HK or our XY? HK. Okay. HK. So steps 2 and steps 3 are the HK and the XY points. So then the next step for your XY says to Peter Piper picked a is to pick a pretty point. That means any point, you can use any point on the graph, preferably one with integer values, and for your convenience, 2 have been marked for you. I'm going to choose this one, the 5, 0. It does not matter which point you choose. As long as your math is good, you'll get the same answer as a person who picks a different point, a different XY. And this is your XY values right here. So we're going to plug those in. What will I be plugging in for Y? 0. What will I be plugging in for A? Nothing. Good, because I'm trying to solve for A. Absolute value bar. What goes in for X? For H? For K? 2. Okay. And then the next step is to solve for A now. What math do I need to do first, next? Inside the absolute value, right? The 5 minus 1. When we did absolute value way at the first unit when we were reviewing it, a lot of times people would take the absolute value of 5 and the absolute value of 1, or they would sort of interchange things. But what you want to do is simplify inside completely before you take the absolute value. And so that will give me 4 inside there. And then now you do absolute value. What's the absolute value of 4? 4. Okay. So that gives me 4a plus 2. And then after that, it's really easy. Subtract your 2 from both sides. Divide by the 4. And a is negative 1/2. How come I'm not done? I mean, I feel like I'm done. I found an answer. I'm not. What are we trying to get? What are we trying to get? Not just a, but the equation, right? So the last step then is to plug the things that are constant, plug them back in to step 1. So that is, the things that are constant are the a value, the h, and the k. So those things go back into the general form that you found in step 1, but you're leaving x and y as x and y, because they represent the infinite amount of points on the line, any point x, y. So it's y equals a, which is now negative 1/2, absolute value of x minus h, which was 1, and then plus k, which is 2. And that's it. Okay. And another reason why you always want to do the work, even if you can do it in your head, is sometimes that you think the stretch or compress is an integer value, but it's not. It's actually a fraction. And the algebra will show that to you when your eyes might have played tricks on you. So you do. So that's another reason to always show your math.